Hey everyone, welcome back to my daily coding series. Today is day 82. So I'm going to look at going down this roadmap here. So I'm going to look at this problem here, a hard stack problem called the largest rectangle in histogram. So I'm going to spend some time with this problem and see where I get. All right, so we're given an array integers heights where each element is a height. And the width is 1. Return the area of the largest rectangle that can be formed among the bars. This chart is known as a histogram. Okay, so we want the largest area that can be formed among the bars. So if we were to visualize this, okay, so I'm going to draw this out, so bear with me here. So this is 0. So we'll have 2. Let's look at the second example, I guess. So 1, 3, and then this is 7, 5, 6, 7. Okay, so basically this information, 137, is represented here. So we have to get the max area. Return the area of the largest rectangle that can be formed among the bars. So I'm guessing here. So here is a rectangle of size 6. That one. This is a rectangle of size 3. This is a rectangle of size 3. And this is a rectangle of size 7. Interesting. And now for the other one, so if we look at this, it may be easier if I draw the histogram sideways. So 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3, 4, 5, 6, 7. 1, 2, 1, 2, 1, 2, 3, 4. Okay, so this is the first test case, but the x-axis is rotated 90 degrees in this case, just so it's easier to type. Okay, so in this case, we look at all the rectangles and we find this rectangle here of size 8. So this is like asking the question, how many columns, if these are columns in this case, how many columns have size 2? So we're saying, like, we know at least 4 columns in a row have height equals 2. So then 4 times 2 equals 8. We can also say at least 1 column in a row has height equals 7. So that's like 1 times 7. So we can kind of make these different metrics. So with the first height, okay, so this is interesting. So the first height we know is 7. So let me just copy this over. Okay, so the first height is 7. So this makes me think that so either we encounter something that's equal to 7 or greater than 7. So if we encounter, or less than 7. So also we can use everything's height. So if we have heights of, so it's actually pretty similar to the last problem I did yesterday with the rainwater, but if we have a height of like 5 and 6, the max area here would be the minimum of that times 2. So we have, it's like the minimum, yeah, huh. Do they all have to have at least height of 1? No, they could have a height of 0. So it's like we want to find the minimum height of a subarray and multiply the length of that subarray by the minimum height. So I guess what we could do So the brute force would be for every subarray, calculates the min value and multiply by the length. So this might be an interesting way to do it. So basically what I'm doing is taking every subarray and then finding its max area and then just taking the biggest one that I find. But there is some interesting stuff. Because it's like, okay, so if we keep going, so when we encounter 7, our max so far is 7. When we see 7, 1, we like the next rectangle that we just got access to is of size 2 because it's the minimum of these times the length of it. So it's 1 times 2. Then we keep going here, and now it's the minimum of these times the length of it, so that would be 3. And then we could keep going. It's the minimum times the length would be 4, right? And then 5, and then 6. So then we could try starting here and doing the same thing, and then here. Is that bound to give us one of the answers? Yeah, so what if we wanted to stop? So if we had like 7, 7, 1, in this case we would say, okay, we have 14, and then adding this would give us only 3. So my question is, like, how do we know when to reset? 7, 1. You can calculate this. So if we had 7, 7, 1, 2, 2, 4. So we'd calculate this, and then this, and then this. Yeah, so I'm trying to think, is there a different way to do it besides every subarray? Like, is there some inherent part of the problem that means that we don't have to do every subarray? And I'm not sure because, you know, this could just as easily be that. And then in this case, we'd want to start here and end here. Okay, so I'm very confident I could code the brute force solution. Very confident I could do that. So this would basically be, so however many subarrays there are in this, which basically at every decision we can either include something or not. So it's 2 to the power. So this solution would be 2 power n. So pretty slow. Obviously this is a stack problem, so there has to be some sort of stack nature in here. We could do multiple pass-throughs as well. I don't know if there's any like dynamic programming elements of it. Like, okay, so for instance, we know like if we had 7, 7, and then 6. So this area is 14. And then we know that when we see a 6, the area of this triangle using the previous one would be 14 minus how much we just lost times the length. So it would be, in other words, like 14 times 7 minus 6 times 3. Sorry, 14 minus. So this would evaluate to 1, and it would give us 14 minus 3, which is 11. But I don't think that's true, because it would give us... Well, it would just like update the minimum. So I'm thinking like whenever we encounter a smaller number, we update that minimum. Or we update, so okay, so when we just have 7, we say like max found so far is 7, the minimum, okay. So basically the formula is the minimum of the subarray times the length of the subarray. So when our subarray is just 7, it's 7. When it's 7 and 7, it's 14. When it's 7, 7, 6, it is 6 times 3, 18. And also too, like if you have all ones, this length becomes important. But then that brings me to my case of like 1, 7, 7, 6. So how could we use a stack here to know? I guess maybe since we've increased, like maybe we can think if this formula is less than if we just started a new rectangle, well, not necessarily. My question is like, how do we know when to start a new rectangle? So if we look at 7, 7, 1, 7, 2, 2, 4. So we have 7, and then we get to 1. So I would say at this point, the largest we can get is 7, and then here the largest we could get is like, I guess 2. Of course, so like if we include, yeah, so it would be like the subarray at this position. All right, and the subarray at this position would be 3, and then 4, and then 5, and then 6. If we do it from the back, it would be 4, 4, 6. So, and then 8. Yeah, so doing it from the front or back doesn't really matter. We'd have to do it from every position. Yeah, so I'm thinking, could we do 2 n squared pass-throughs? Basically, my thing is, like, I want to start at every position, right? So we would start here, continue it. Then we'd start here, continue it. Start here, continue it. Start here, continue it. Start here, continue it. And then this way, we would do start here, continue it. Start here, continue it. Start here, continue it. Start here, continue it. Yeah. So, what is this problem basically? It's find the subarray with biggest score, where the score is the minimum of that subarray times the length of that subarray. So that's like another way of find the subarray with the highest score, where so the minimum element in that subarray times the length of that subarray. So is there some heuristics we can make? So we probably want to maximize the minimum value. And we want to increase, so we want to maximize both of these elements. All right, let's think in terms of stacks. So if we have a stack, I'll add 7 to the stack. And then I guess if we have something that's bigger, so if we had like 7, 8, 9, so let's look at these, 9, 8, 7. So if we had 7, 8, 9, would we just like add to the stack, and then when we get to the end, or do we add new minimums? Could we also think of like how many subarrays exist with every height? So like we can see there's only one subarray with a width of 1, and that's everything. Width of 2, it's everything that's split by 1s. Width of 3 is everything that's split by elements that are less than 3. So like, if we cut out these 1s and 2s, the remaining would have a width of, well, would have at least a minimum height of 3. So 1 is the smallest element. 2, you would include everything. So maybe you could like keep track of your elements. So you'd have like 1, 2, 4, and 7. And we'd say, okay, for height of 1, we're going to like continuously add to the stack until we are less than 1. So we'd add 7, 1, 7, 2, 2, 4. And then, okay, our answer would just be the sum, or it would be the length of this times our element. So let's just say like element, or I guess we could say like I equals 1. And then if we have I equals, so we'll go to the next element, and I'm not sure if it has to be like sorted or anything like that. So this will basically be, so it's not really a stack, but we're like adding to it, and then, okay, so here, we just have 7. Because 1 is less than 2. So we know that this won't even have, so we could make this a rectangle of size 2 right here. We could make this a rectangle of size, so maybe we start with 7. Let me try starting with 7. So if we start with 7, basically, so we'll add anything that's greater than or equal to 7. So we'd say, okay, our possible towers with 7 height are 7. Then we skip this, and 7. Then for I equals 4, our possible rectangles with height 4 are, again, 7 and 7. Now for height 2, we would say we can make something of height 2 at just 7. And then for the next stack, we would do 7, 2, 2, 4. And then for I equals 1, we would say stack equals 7, 1, 7, 2, 2, 4. And then we would find, the biggest length. And we wouldn't even really need a stack here. We would just use a count. So this would basically have to, so the runtime of this algorithm would be, for every unique element, we have to traverse this. So I think it would be, in this case, the runtime of this algorithm would be the number of elements. So like h, well, the number of, it'd be like h times n, where h is all of the different heights and n is the length of the heights. So this would be like the unique elements. So it would basically kind of be like n squared. So that's an improvement, and we don't even need stack. So we could just use a count for this. Okay, but we're looking for linear time and space. Okay, so this is interesting because, so basically you just count for every unique element, you count the longest subarray in which you don't go beneath that lowest element. And then you just multiply the count by whatever element you're at, assuming that this is the minimum. And yep. So here you'd multiply 1 by the count of this, here you'd multiply 2 by the count of this, 4 by the count of 1, and 7 by the count of 1. So that's really interesting, and that's n squared. So, and I'm not even using a stack, I'm just using a single count here, even though it says stack. So basically it has constant space actually. So now the question is, I want to take less time but use more space as a trade-off. So what information can I store so that we don't need to do for every single thing? So for 7, 1, 7, 2, 2, 4. It's kind of like we have to keep track of multiple different rectangles at a time because there is this underlying rectangle where all the heights are 1, but there's also additional rectangles. I don't know if the 1 is just a base case. I feel like it's not, because of course you could just multiply the length of this by the minimum element, but I feel like if you could make the minimum element like a variable like I did in this case, you could get some good results. 7, 1, 7. So, okay, so let's imagine that all we know is 7. So let's just imagine that the only thing we can see is 7. So if the next element is 1, that tells us that right now we have basically two rectangles going on. So we have the rectangle of 7, and then the rectangle of 1, and then So we actually sort of have like 3. So we have just 7 by itself, just 1 by itself, and then their horizontal, which is 2. Okay, so then when we add another element, which is 7, so now we have another rectangle. So this one would be updated to 3, and then we have another 7 as well. Then we add another element called 2. So this element gets updated to 4. These are the same. This is the same. So 4. But now we have a new rectangle starting to form. So we have a new rectangle starting to form, which is one in which the minimum element is 2. So we have 4 if we take 1 from all of them, but we also have 4 if we take 2 from just these 2. So I'm wondering, we might not need to store the 717. So that's already in the answer for us. So 7, 1. So the only one we need to store is here. So 2. So okay, so let's imagine we have this. So we need to store the horizontal rectangles. We need to store the horizontal rectangles. So first, the horizontal rectangle is of size 1, just the length. Then when we add 1, the horizontal rectangle is of size 2. When we add 7, well, honestly, wait. So right now, of 7, it has a width of 1. Yeah, so it has a width of 1 and a height of 7. Okay, when we add 1, a new rectangle forms, which is the connection between these two. So obviously we have 7 and 1 are the horizontal with 1 width only, but we also have another one with 2 width and size and height of 1, so that's 2. So then we add 7. So that, of course, is its own rectangle. A horizontal between all 3 is of size 3. Then we have 2. So when we add 2, that's another vertical rectangle of size 2. This subarray still has 4, but now we can use, so when we introduce 2, we can use the fact that because 2 is less than 7, that this horizontal rectangle is now combined has a height of 2 and a width of 2. So that's also 4. So at this point, I don't know if there's any way to tell which rectangle will prevail, I guess. Okay, so then we have 2. So in this case, so we see that 2 is the same as 2. So that means it can be a part of our rectangle. And we don't have to retroactively shrink anything. So then at this case, we would just add, so because it's, yeah, so every time you introduce a greater element, I think that's when you want to possibly start a new triangle. Or sorry, a rectangle. So 2 and then 4. So I think maybe, so every time you add a larger element, that is a, so that element is a possible new start to a rectangle. So every bigger element that you add is a possible new start. But if you go beneath, so if you have something like, let's say, 7, 8, 9, and then 6, or like, let's say 3. So when you see 7, you say, okay, this could be a new start to a rectangle. You see 8, and you say, okay, if you see 8, my idea is if all of these are bigger than 7, so like if we have like, let's say we have 100, 100, 100. So 7 and then 100. So this would be only 14. Whereas this could be a start of a new rectangle. Let's say it was like 10, 10, 10. Because then we could have 10 times 2 instead of 7 times, well, okay, let's say it's 5. So 5 times 2 is 10. I'll just pick 4. Okay, so 4 times 2 is 8. So this would be 8. But because we see a 10, that means there is potential that we start a new rectangle because 10 times 2 is 20. Okay, so when we see a larger element, that means we could start a new rectangle. Is that ever true if we see a smaller element? So if we had like 10, 4, 10, is it ever true? Let's say this is actually, let's say we have 5, 4, 10. Is it ever true that this is the start of a new triangle? Is it ever true that this is the start of a new triangle? I would say no, because if this was included in the rectangle, sorry, I keep saying triangle. If this was included in the rectangle, we ought to also include the bigger element to the left. So therefore, when we encounter a smaller element, that will never be a leftmost edge of a rectangle. When we encounter a smaller element, that element will never be a new start to a rectangle. We're at 30 minutes, okay. So I'm thinking when we encounter a smaller element, it can never be a new start, because then we would always just include this. So whenever we jump up, it's possible, but not always, that we'll start a new rectangle. So here, it's best to start a new rectangle at 10. But I can think, so now make an example where starting a new rectangle after increasing is not ideal. So here if we have something like 4, 5, 5. So in this case, 5 times 2 is 10, but 4 times 3 is 12. So in this case, it's not ideal to start. It is a possible new start. It's a possible new start. So here it's best to not start upon increasing to 5. So how do we know? Well, maybe every time we increase, we can keep track of that. So our first one we'll consider an increase. So we increased to 4 at index 0. Then we increased to 5 at index 1. And then 5. And then we end at 2. So then we can basically pop off the stack and say, okay, so our final index was 2. So we would say so 5. So that means So we can kind of go backwards and calculate each one. So here, if our final index was 2, I guess it's like 3 technically. So we would say 4 times 3 and 5 times 2. What's the bigger one? Okay, so maybe we do something with that. So and then if we have 4, 10, 10, right? So 4, 0 is our first increase. And then 10, 1 is our first increase. And then our final index is 3. So then it's, 10 times 2 or 4 times 3. Yeah, exactly. So, okay, so what if, so this is good thinking. So I'm thinking like generate stack of increases and select largest starting point. We don't really need the largest starting point, but largest area given starting points. So if we could build this stack, okay, so now let's make up example where we increase then decrease. So still not muted, okay. There. So if we have, let's say 4, 5, 5, 3. We know that when we decrease, so I said when we encounter a smaller element, it will never be the start of a new rectangle. But don't we still need to know that information? So we would say like, okay, we increased at 4, 0, and then we increased again at 5, 1. But then we decrease to 3. So does this element become 3? And does this element also become 3? I think what we do is when we encounter a smaller element, we consider stopping here, maybe. So if we have 5, 4, 3, let's say we have 5, 10, 10, 3. Sorry, 4, 10, 10, 3. So obviously we know the best one is, so we could do 3 times 4, which is 12. We could do 4 times 3, which is 12, or we could do 10 times 2. So the best one is in the middle. So if we do our increases, so we increase index 0 with height 4, and we increase with oh, okay. So we would increase. Okay, so this is interesting. So we increase here, and then once we get to a stopping point, so let's just say we had like a bunch of random stuff here. So once we get to something that's less than, we should probably calculate this. So we'd say like final index, in this case, is 0, 1, 2, 3. So we would find like max so far equals basically 2 times 10, which would be 20. So, but then what do we put in our stack when we continue? So like, what if there was a 2? So this would become 1 and this would become 2. So we would, and then we'd have 2, 0. So would we continuously pop until, so maybe we could keep popping off the stack until we reach something that's less than our element. And then we would say, well, 3, so then we'd say 2, 0, and now it's 3, 1. 3, 1. So when we got here, we continuously pop off the stack until we reach something that's less than. So our stack will always have increasing elements. And then when we encounter something that's less than, we pop all the elements that are greater than. So like if we encounter a number x, we pop everything off the stack that's greater than x and stop when we encounter something that's less than x. Yeah. And then we keep logging so let's imagine this was like a billion ones. Okay, so it's just like a billion ones. Let's say it's 100 ones. Okay, so then our final index, actually let's say it's 100 threes. So our final index would be 0, 1, 2, 3, 4, like 104 or something like that. So once we reach the end, we never increased again. So we would never add a new element to the stack. So then we would just say, okay, what's bigger? 104 times minus 1 times 3 or 104 times 2? Right, so, okay. So I think that may work. So, all right. So if you encounter a like a bigger number, add to stack with index. If you encounter smaller number, pop from stack until x is biggest number. And make sure you keep, make sure you add x and then like y to stack, where y is the last, where it is the index from the last popped element. So in this case, 1, right? Because we're saying with size 3, we can go actually all the way back to 4. Okay, let's try coding this. So I'm not exactly sure. So this may be, how much time? We're at 40 minutes. Okay, so this may be, it's, I think it's linear because, so we either increase to the stack. So every element gets increased, it gets added to the stack and then popped from the stack eventually. So I think that would be linear because it's only 2 adds and 2 pops per element. Or sorry, 1 add and 1 pop. Okay. So we have heights. Okay. So we have heights. And we have a stack. So, and we'll say, so like top element, it starts at, I guess, 0. And then what we'll say is for height in heights, if height is greater than top element, if it's greater than top, so all right, let's enumerate this because we want the index value. Okay, so if so if the height is greater than the top element, then what we want to do is say stack dot append the tuple height and I. So I'm doing the height and then the index. Sounds good. Yeah, so just keep doing that. Otherwise, yep, so if it's less than or equal to, well, if it's equal, do we want to do anything at all? We don't really want to pop. So, okay, so if the height is less than is it the top element, or is it just any time we decrease that we have to pop from the stack? So we add, do nothing, and then we decrease. What if there was, well, I guess it's just any time we decrease, but that also means it's any time we are less than the top element. So yeah, because if we had, let's say like 2, 4, 3, no matter, okay, so if we have a number x, this statement has to be true. It has to either be bigger than the top element or less than or equal to the top element, but it can't be, it's impossible for it to be less than the top element but like bigger than the previous element. So the top element is really just like the most recent element. Okay, so if it's less than the top element, then while the stack has anything at all, we want to, okay, so while stack and, so we want to continuously pop, and and height is greater than the top of the stack's height. So if I'm a number and I'm bigger than, no, if I'm less than, yeah, while I'm less than, or equal to, I think. So I'll make a note of that. Okay, so while I'm less than or equal to, I want to continuously pop from the stack. And I'll say, so like hi, no. So we'll pop stack. And we want to calculate, so like old, so previous height and previous index equals stack.pop. So this is a tuple and it gets unpacked. And we need to know I. So let's have result. And then we'll say result equals the max of itself. And so whatever I that we're at currently. So if we have like 2, 0, or let's say we have this example is good. So if I index this 0, 1, 2, 3, 4. So we decrease at index 4. Okay, so this would be our stack. So when we get to index 4, we would say that, okay, this is less, so we go from 2 to 4, so 4 minus 2. So it'd be like I minus previous I, that's the length. And then we'll multiply that by, so we would say like area is I minus previous I times previous height. And we'd say our area, if it's bigger than the biggest one we found so far, so like max area found. Okay, so we'd keep doing this, and then eventually, so we'd say, okay, 4 would calculate the area for this, so that would be area equals 4 minus 2 times 10, so it'd be 20, and then, so we'd store that, we'd say, all right, we're still 3 is still less than or equal to this. So we will add, so we'll say previous I, so area equals 4 minus 1, so 3 times 4, which is 12. We update that, and now this is not true because 3 is not less than or equal to 2. So at this point, we want to add to the stack, actually. So we want to say stack.append, and what do we want to add? We want to add height. We want to add height 3, and whatever we previously just popped, like that index. So now if we had 2, if we found 2 again, then our index would be 5. Okay, so we'd add this, then we'd go back up, and we'd say that the height 2 is less than, okay, top element also has to be updated. I think we could just say like this. It's really just previous. Oh, that's not a good word. Okay, I'll just keep it top element. So then we'd say, okay, we went down again. Height is less than the top element. So in this case, now this is true. So height which is 2 is less than stack of a negative. The top of the stack is height. So 2 is less than 3. So then we'll say area equals I, which is 5, minus 1, 4. So this is 4 times 3, 12. It should be, it should be 5. It's actually 5 minus 1 now. So it's 5 minus 1, so 4. So it's 4. 4. Okay, let's see here. So and now it'll say, okay, the area here. Oh. But it's not actually, yeah, it's previous height. But it should actually be current height, I think. I think this should be height. Should it not be? The reason is well, we're calculating for that one. Okay, so what does this do? Previous height and previous I. So previous height is 3 and previous I is 1. Area equals I, 5 minus 1, so that's 4 times previous height, which is 3. So 4 times 3 is 12. So why is it's giving us 12? And we'd pop that. 12. 12. I thought we already kind of calculated that though. So maybe we don't need this part. Okay, so then this would, let's just assume so then what would that would just give us, okay, so we're still in the while loop actually. So it goes back up and it says height of 2 is less than or equal to this 2. So then previous height is 2, previous I is 0. So then area equals 5 minus 0, so 5 times previous height. So this is just 5 times 2. Well, if it's equal to it, then we should do plus 1. Because if it's equal, then we want to include... Yeah, that makes sense. If it's equal in this case, then we would want to include... So, I mean, would we just say if... So we would add like one more. So if height equals stack of -1. So I'm just thinking if they're equal, then we would want to... Alright, I'm going to go get a drink of water. I'll be right back. Alright, I'm back. So I only have a couple more minutes left. So I think I was getting a bit lost. But also like kind of on the right track. Okay, so we have 2, 0, 4, 1, 10, 2, and then I'm just gonna assume that if we do the same thing, it doesn't really change it. Okay, now we get to 3. So my idea is, so we do 4, so to calculate this, you do 4 minus 2, because it's not included. 4 minus 2 times 10, right? So that would give you 20. And 3 is still less than, so you'd get 4 minus 1 times 4, which is 12. And then at this case, it's greater than, so we stop. Then when we encounter 2, so I think we don't really have to add it back to the stack at that point. Maybe we should, though. I feel like we should, because then we're never really doing the calculation 4 minus 1 times 3. So maybe we should just also add, like when we do that here, we could also add that area, so it would be like, maybe instead of appending it to the stack, like maybe we do that, but or maybe we just add that calculation. So we say it equals the max of, not muted, right? Okay, so, and then area. So what is that? It's just going to be I minus previous I times the current height this time. So it's like 4 minus 1 times whatever the current height was, because this was the last element. Okay, then we get to here. So it's equal to this. So now I'm saying, so we'll do 5 minus 0 plus 1 times, if they're equal, you could do either height. All right, and then we just return max area found. So I'm not really expecting it to work off the bat. If our stack is empty, how is this? So stack must have at least one element in it, though. So I'm not sure how that's empty. Stack of -1. This should give me the last element in the stack, I believe. So I'm not quite sure why it's not doing that. So I just want the last element of the stack. Okay. Is it this? Is it that? Line 61. Line 155, line 1. Line 61. If height equals, so it's right here. Is it because I pop from the stack? I see. I see. So I should just say previous height here because I already popped. Okay. Yep, that makes total sense. So that bug is fixed. I don't know if that was the only bug. There's always more bugs. Okay, so I output 7, but the expected output is actually 8. So let me print here, like, let me just see what it's calculating. I'm kind of out of time, to be honest, but okay, so it calculates, so 7, 0, and that's an area of 7. And then for 1, it decreases. Okay, yeah. And then for 7, and then when it comes to 2, the stack is 7, 2. Is that what it should be? Okay, so we add 7, 0, then we pop. We should pop 7, 0. Yeah, we do it here. And then the new stack, so area 7. Okay, then we add 7, we pop from the stack. Our stack is just empty. So why isn't it, so when we go to 2 to 2, that doesn't do anything. And then we add 4. Oh, I think we also have to do this whole popping routine when we're done also. Because if it's the last element, what about the other one? The other one doesn't work? Yeah, so in both these cases it looks, so if we like always increase, we never pop from the stack. So I want to like just do this again. So while stack, what I'll do is so we'll just say like previous height, previous index equals stack.pop. And then we'll just say, so because these are all increasing, yeah, we don't add if it's equal, right? Yeah, so these are all increasing. So times previous height, basically like that. So this would get rid of the times at the beginning. 7. Print the stack at the end. The stack here is 4, 5. So why does it not? Area is 0. Area is 1. So when we pop here, it should be, oh, is it doing 2 minus 2? So should this actually be plus 1? Okay, so that fixed that one. So this one is saying, okay, it's an area of 7. This is an area of 6. That's correct. This is an area of 3. Okay, so that's working perfect. So what about this one? It looks like this is not adding to the stack properly because maybe it should actually have a, so it's calculating 7. So maybe I should actually be adding 2 back into the stack then. Okay, I have to go for now. I might be back. I will be back hopefully, so alright, I'll be back.